Hello. We're here. It's Monday, and we're here to continue our studying, even though, we're here today and the schedule has changed, so I urge you to look at it. I shared it on, I think, Twitter and the community page, so do look at it. Yes, double checking. Oh, there, I did share it. And yeah, today it feels like autumn for the first time for me. So that's pretty nice. Let's start. I forgot to say good morning, good afternoon, good evening, and if it's night, either go to sleep or I don't know. Well, let's start with a recap. We have been taking this course from fast.ai called Introduction to Machine Learning, and it's taught by Jeremy Howard, and we are, as you can tell by the title, trying to open this app, there we go. As you can tell by the title, we are in we're actually going to start lesson 6 today. So it's been like, I don't know, like 15 days, 16-ish days. We did lesson 1, 2, 3, 4, 5, and we're starting lesson 6 today, and we had our F from scratch. That was really cool, from yesterday's lesson, so I really enjoyed that. And now we're starting lesson 6. In lesson 6 we have data products and live coding, so that will be interesting. In the first half of today's lesson, we'll learn about how to create data products based on machine learning models. Now that's cool. The data-driven method based on the data-driven method, and in particular how model interpretation is an important part of this approach. Next up, we'll explore to be fun. Okay. Is there something wrong with the internet? Oh, there's definitely something wrong with the internet. 60% drop rate? Let me monitor this. Okay, 50% drop rate is actually durable, I hope. And let's start lesson 6.
So we've looked at a lot of different random forest interpretation techniques, and a question that's come up a little bit on the forums is like, what are these for, really? Like how do these help me get a better score on Kaggle? And my answer's kind of been like, they don't necessarily. And so I want to talk more about, like, why do we do machine learning? Like, what's the point? And to answer this question, I'm going to put this PowerPoint in the GitHub repo so you can have a look. I want to show you something really important, which is examples of how people have used machine learning, mainly in business, because that's where most of you are probably going to end up after this, is working for some company.
Okay.
I'm going to show you applications of machine learning which are either based on things that I've been personally involved in myself or know of people who are doing them directly. So none of these are going to be like hypotheticals. These are all actual things that people are doing and I've got direct or secondhand knowledge of. I'm going to split them into two groups, horizontal and vertical. So in business, horizontal.
Oh, I was about to ask what they are, but he's explaining it, so I should shut up.
Means something that you do like across different kinds of business, whereas vertical means it's something that you do within a business or within a supply chain or within a process. So in other words, an example of horizontal applications is everything involving marketing. So like every company pretty much has to try to sell more products to its customers. And so therefore does marketing. And so each of these boxes are examples of some of the things that people are using machine learning for in marketing. So let's take an example, right? Let's take churn. Okay. So churn...
okay. Marketing applications. That's a weird name. I really don't know any of these. Okay.
Refers to a model which attempts to predict who's going to leave. Right? So I've done some churn modeling fairly recently in telecommunications. And so we're trying to figure out for this big cell phone company which customers are going to leave. That is not of itself that interesting. Like building a highly predictive model that says Jeremy Howard is almost certainly going to leave next month. It's probably not that helpful because, like, if I'm almost certainly going to leave next month, there's probably nothing you can do about it.
I think, nothing you can do about it. I thought it would be like, how can we, I wouldn't say make him stay, but like encourage him to stay would be more useful. Knowing who is going to leave and the why, if possible, that would be really good.
Right? It's too late. It's going to cost you too much to keep me. Right? So in order to understand, like, well, why would we do churn modeling? I've got a little framework that you might find helpful. So if you Google for Jeremy Howard data products, I think I've mentioned this thing before. There's a paper you can find, Designing Great Data Products, that I wrote with a couple of colleagues a few years ago.
That's interesting.
And in it, I describe my experience of actually turning machine learning models into like stuff that makes money, right? And the basic trick is this thing I call the drivetrain approach, which is these 4 steps. The starting point to actually turn a machine learning project into something that's actually useful is to know, what am I trying to achieve? And that doesn't mean like I'm trying to achieve a high area under the ROC curve, or I'm trying to achieve a large difference between classes. No, it would be I'm trying to sell more books, or I'm trying to reduce the number of customers that leave next month, or I'm trying to detect lung cancer earlier. Right? These are objectives. So the objective is something that absolutely directly is the thing that the company or the organization actually wants. No company or organization lives in order to create a more accurate predictive model. Right? There's some reason, right? So that's your objective. Now that's obviously the most important thing. If you don't know the purpose of what you're modeling for, then you can't possibly do a good job of it. And hopefully people are starting to, pick that up in out there in the world of data science. But interestingly, what very few people are talking about, but it's just as important, is the next thing, which is levers. A lever is a thing that the organization can do to actually drive the objective. So let's take the example of churn modeling, right? What is a lever that an organization could use to reduce the number of customers that are leaving?
Lever and leaving. Okay. And what does the lever do? Like, is it tuning parameters? What is that?
They could take a closer look at the model and do some of this random forest interpretation and see some of the causes that are causing people to leave and potentially change those issues in the company.
Yeah, the why.
Okay, so that's a data scientist answer. But I want you to go to the next level. What are the things? The levers are the things they can do. Do you want to pass it behind you? What are the things that they can do?
Just outreach, like calling or sending emails.
They could call someone and say, like, are you happy? Anything we could do? Okay.
They can provide incentives to increase engagement with the product.
Yeah, so they could, like, give them a free pen or something if they, buy $20 worth of product next month. Yeah.
Okay.
You are going to do that as well? Okay, so you guys are the giving out carrots rather
Everybody's giving out pens.
than the handing out sticks. You're going to send over in a couple of goes.
Change the price of the product or the subscription, or
Yeah, you could give them a special. All right. So these are levers, right? And so whenever you're
I don't know why my brain went. Levers are like for stopping trains, because he was talking about trains. Oh, hi. What's up? I'm the one with... it's okay. It is live. We have internet. Thank you. Yeah, internet issues are just a part of life. Yeah, I know. I know. Yeah, I'm not scared. No worries. Yes, I can tell that you can see my avatar. Thanks. I chose it because I thought it looks cool.
working as a data scientist, keep coming back and thinking, what are we trying to achieve? We being the organization, and how are we trying to achieve it? Being like, what are the actual things we can do to make that objective happen? So building a model is never, ever a lever, okay? But it could help you with the lever.
Could understand you what to do, right?
So then the next step is, what data does the organization have that could possibly help them to set that lever to achieve that objective, right? And so this is not what data did they give you when you started the project, right? But like, think about it from a first principles point of view. Okay, I'm working for a telecommunications company. They gave me some certain set of data, but I'm sure they must know where their customers live, how many phone calls they made last month, how many times they called customer service, whatever. Like, and so have a think about, like, okay, if we're trying to decide, like, who should we reduce the, give a special offer to proactively, then we want to figure out, like, what information do we have that might help us to identify who's going to react well or badly to that. Perhaps more interestingly would be, what if we were doing like a fraud algorithm, right? And so we're trying to figure out, like, who's going to, like, not pay for the phone that they take out of the store. They're on some 12-month payment plan. We never see them again. Now, in that case, the data we have available, it doesn't matter what's in the database. What matters is what's the data that we can get when the customer's in the shop, right? So there's often constraints around the data that we can actually use. So we need to know, what am I trying to achieve? What can this organization actually do specifically to change that outcome? And at the point that that decision is being made, what data do they have or could they collect, right? And so then the way I put that all together is with a model. And this is not a model in the sense of a predictive model.
So we're still collecting data that feeds to that model, but it's not the data that they give us, because we don't trust them.
Model, but it's a model in the sense of a simulation model. So one of the main examples I give in this paper is one I spent many years building, which is if an insurance company changes their prices, how does that impact their profitability, right? And so generally your simulation model contains a number of predictive models. So I had, for example, a predictive model called an elasticity model that said for a specific customer, if we charge them a specific price for a specific product, what's the probability that they would say yes, both when it's new business and then a year later, what's the probability that they'd renew? And then there's another predictive model, which is what's the probability that they're going to make a claim and how much is that claim going to be, right? And so like you can combine these models together then to say, all right, if we changed our pricing by reducing it by 10% for everybody between 18 and 25, and we can run it through these models that combine together into a simulation, then the overall impact on our market share in 10 years' time is X, and our cost is Y, and our profit is Z, and so forth, right?
Okay.
So in practice, most of the time, you really are going to care more about kind of the results of that simulation than you do about the predictive model directly. But most people are not doing this effectively at the moment. So for example, when I go to Amazon, right, I read all of Douglas Adams's books, right? And so having read all of Douglas Adams's books, the next time I went to Amazon, they said, would you like to buy the collected works of Douglas Adams? This is after I had bought every one of his books.
That's happened to me like a bajillion times, where you buy something and then they give you, do you want to buy another one of the, like the, you know, like you buy, I don't know, something, like I bought a projector off of Amazon, and then they're like, here are other projectors. Like, dude, I got a projector. I'm not gonna buy another one the next day. So, good point.
From a machine learning point of view, some data scientist had said, oh, people that buy one of Douglas Adams's books often go on to buy the collected works, right? But recommending to me that I buy the collected works of Douglas Adams isn't smart, right? And it's actually not smart at a number of levels. Like, not only is it unlikely I'm going to buy a box set of something of which I have every one individually, but furthermore, it's not going to change my buying behavior. Like, I already know about Douglas Adams. I already know I like him. So taking up your valuable web space to tell me, hey, maybe you should buy more of the author who you're already familiar with and have bought lots of times, isn't actually going to change my behavior, right? So what if instead of creating a predictive model, Amazon had built an optimization model that said, like, that could simulate and said, if we show Jeremy this ad, how likely is he then to go on to buy this book? And if I don't...
Yeah, it's a recommender system, but I feel like there has to be some point where they say, okay, recommender system for things the person hasn't seen, and like he said, optimization system for things the person has, like, you know, just bought, categories of things that are bought, you know.
Show him this ad, how likely is he to go on to buy this book? And so that's the counterfactual, right? The counterfactual is what would have happened otherwise. And then you can take the difference and say, okay, what should we recommend him that is going to maximally change his behavior, so maximally result in more books? And so you'd probably say, like, oh, he's never bought any Terry Pratchett books. He probably doesn't know about Terry Pratchett, but like lots of people that liked Douglas Adams did turn out to like Terry Pratchett, so let's like introduce him to a new author.
Didn't Terry Pratchett write the final Douglas Adams Hitchhiker Guides to the Galaxy book? I like Terry Pratchett, I like Douglas Adams, I like Neil Gaiman. All of those are British sci-fi-ish authors. I haven't actually read any, just like Terry Pratchett books. I've read things that he's collaborated with, like Angels and Demons, like I don't know, which is it the restaurant at the end of the universe? Anyway, not what we're talking about. Tangent, sorry.
Right? So it's the difference between a predictive model on the one hand versus an optimization model on the other hand. So the two tend to go hand in hand, right? The optimization model basically is saying, well, first of all, you have a simulation model, right? The simulation model is saying, in a world where we put Terry Pratchett's book on the front page of Amazon for Jeremy Howard, this is what would have happened. He would have bought it with a 94% probability, right? And so that then tells us with this lever of like, what do I put on my homepage for Jeremy today? We say, okay, of all the different settings of that lever, the put Terry Pratchett on the homepage has the highest simulated outcome. Right? And then that's the thing which maximizes our profit from Jeremy's visit to Amazon.com today. Okay? So generally speaking, your predictive models kind of feed in to this simulation model, but you've kind of got to think about like, how do they all work together? So for example, let's go back to churn, right? So I'd turn out that Jeremy Howard is very likely to leave his cell phone company next month. What are we going to do about it? Oh, let's call him, right? And I can tell you, if my cell phone company calls me right now and says, just...
If I can, I wouldn't pick up, and like, I'd be terrified, like, don't leave.
calling to say we love you, I'd be like, I'm canceling right now. like that would be a terrible idea. So
just calling to say, ooh, no thank you.
Again, you would want a simulation model that says like, what's the probability that Jeremy is going to change his behavior as a result of calling him right now? Right? So one of the levers I have is call him. On the other hand, if I like got a piece of mail tomorrow that said like, for each month you stay with us, we're going to give you $100,000. Okay, then that's going to definitely change my behavior, right? But then...
I guess not all the inputs in the lever thing are financially sound. The 100,000 one is not the best choice, but it will make him come back to you running.
Feeding that into the simulation model, it turns out that overall that would be an unprofitable choice to make. So do you see how all this fits in together, right? So when we look at something like churn, we want to be thinking like, what are the levers we can pull, right? And so what are the kind of models that we could build with what kinds of data to help us pull those levers better to achieve our objectives? And so when you think about it that way, you realize that the vast majority of these applications are not largely about a predictive model at all. They're about interpretation. They're about understanding what happens if, right? So if we kind of take the intersection between, on the one hand, here are all the levers that we could pull, like here are all the things we can do, and then here are all of the features from our random forest feature importance that turn out to be strong drivers of the outcome. And so then the intersection of those is, here are the levers we could pull that actually matter. Right?
Because you can pull some levers that don't matter, like the one for that Kronk pulled in, what's that cartoon called? Emperor's New Groove, yeah, where they fall.
Because if you can't change the thing, then it's not very interesting. And if it's not actually a significant driver, it's not very interesting, right? So we can actually use our random forest feature importance to tell us what can we actually do to make a difference. And then we can use the partial dependence to actually build this kind of simulation model to say like, okay, well, if we did change that, what would happen, right? So, you know, there are examples, lots and lots of these vertical examples. And so what I want you to kind of think about as you think about the machine learning problems you're working on is like, why does somebody care about this, right? And like, what would a good answer to them look like? And how could you actually positively impact this business? So if you're creating like a Kaggle kernel, try to think about from the point of view of the competition organizer. Like, what would they want to know? And how can you give them that information? So something like fraud detection, on the other hand, you probably just basically want to know who's fraudulent, right? So you probably do just care about the predictive model. But then you do have to think carefully about the data availability here. So it's like, okay, but we need to know who's fraudulent at the point that we're about to deliver them a product, right? So it's no point like looking at data that's available like a month later, for instance. So you've kind of got this key issue of thinking about, the actual operational constraints that you're working under. Lots of interesting applications in human resources, but like employee churn, it's another kind of churn model. We're finding out that Jeremy Howard's sick of lecturing, he's going to leave tomorrow. What are you going to do about it? Well, knowing that wouldn't actually be helpful. It'd be too late, right? You would actually want a model that said, what kinds of people,
catches people who are even like burnout. That would be really cool.
Are leaving USF. And it turns out that like, everybody that goes to the downstairs cafe leaves USF, I guess their food is awful, or, whatever, right? Or everybody that we're paying less than $500,000 a year is leaving USF, because they can't afford basic housing in San Francisco.
Wow.
So like you could use...
It's a good thing I don't live in San Francisco.
your employee churn model, not so much to say like which employees hate us, but why do employees leave, right? And so...
Yeah, so finding the why is your job.
Again, it's really the interpretation there that matters. Lead prioritization is a really interesting one, right? Like this is one where a lot of companies... yes, Dina, can you pass that over there?
Yeah, so I was just wondering, so like for the churn thing, you suggested, so one way is like pay an employee like 1 million a year or something. But then it sounds like there are two predictors that you need to predict for. I mean, one the churn and one you need to optimize for like your profit thing. So how does it work with that?
Yeah, exactly. So this is what this like simulation model is all about. So it's a great question. So like you kind of figure out this objective we're trying to maximize, which is like company profitability. You can kind of create like a pretty simple like Excel model or something that says like here's the revenues and here's the costs, and the cost is equal to the number of people we employ multiplied by their salaries, blah 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 blah, right? And so inside that kind of Excel model, there are certain cells, there are certain inputs where you're like, oh, that thing's kind of stochastic, or that thing is kind of uncertain, but we could predict it with a model. And so that's kind of what I do then, is I then say, okay, we need a predictive model for how likely somebody is to stay if we change their salary, how likely they are to leave, with their current salary.
But like, we should have previous data to be able to create a model on this, right? It's not like we decide. I mean, I'm just trying to imagine what sort of data we need. Like, if that company doesn't have a long history, then we'll have to get people from this, like, other available data of people working in the same city, or like the same, if it's like tech or if it's government or whatever. So yeah, it's not like finding everything about that person in a way. It's about finding people in the same situation, right?
How likely they are to leave next year if I increase their salary now, blah blah blah. So you kind of build a bunch of these models, and then you combine them together with simple business logic, and then you can optimize that. You can then say, okay, if I pay Jeremy Howard $500,000, that's probably a really good idea, and if I pay him less, then, it's probably not, or whatever. Like, you can figure out.
Is this a cry for help? That's cute. Yeah, someone needs to pay me. $500,000 is way too much. Too much for me. Like, give me a decent living where I don't have to work 8 hours a day. I think I have the issue of not knowing not knowing how to rest. So someone needs to pay me to rest. 'Cause now I'm like, there's a future. Who knows if it will happen or not? But there's a future where I'll be working full time and be a PhD student, and I probably, I'm scared just thinking about it. Okay. Anyway.
The overall impact. So it's really shocking to me how few people do this. Like, most people in industry measure their models using like AUC or RMSE or whatever, which is never actually what you want. Yes. Can you pass it over here?
I wanted to stress a point that you made before. In my experience, a lot of the problem was to define the problem, right? So you are in a company, you're talking to somebody that doesn't have like this mentality that you have. They don't know that you have to have X and Y and so on. So you have to try to get that out of them. What exactly do you want? And try to go through a few iterations of understanding what they want, and then the data, where the data is, actually where you can measure, which is often know what they want. So you have to kind of get a proxy for what they want. And then, so a lot of what you do is not that much of like, well, some people do actually just work on really good models for, but a lot of people also just work on this kind of, how do you put this as a, classification, regression, or some other type of modeling. That's actually kind of the most interesting, I think, and also kind of what you have to do well, I think.
Yeah, the best people do both. People understand the technical model building deeply, but also understand the kind of strategic context deeply. And so this is one way to think about it. And as I say, like, I actually think, there aren't many articles I wrote in 2012 I'm still recommending, but this one I think is still equally valid today. So like another great example is lead prioritization, right? So like a lot of companies, like every one of these boxes I'm showing, you can generally find a company or many companies whose sole job in life is to build models of that thing, right? So there are lots of companies that sell lead prioritization systems.
Okay. And he's saying that it's lacking information, right? Trying to understand where he's going with this.
Again, like, the question is, how would we use that information, right? So if it's like, oh, our best lead is Jeremy, he's our highest probability of buying, does that mean I should send a salesperson out to Jeremy, or I shouldn't? Like, if he's highly probable to buy, why waste my time with him? So like, again, it's like you really want some kind of simulation that says, like, what's the likely change in Jeremy's behavior if I send my best salesperson, Yanette, out to go and like encourage him to sign. Okay. So yeah, I think this is like, there are many, many opportunities for data scientists in the world today to move beyond predictive modeling to actually bringing it all together, with the kind of stuff that Dina was talking about in her question. So as well as these horizontal applications that basically apply to like every company, there's a whole bunch of applications that are specific to like every part of the world, right? So for those of you that end up in healthcare, some of you will become experts in one or more of these areas, like readmission risk.
Whoa.
Okay, so what's the probability that this patient is going to come back to the hospital? And readmission is, depending on the details of the jurisdiction and so forth, it can be a disaster for hospitals when somebody is readmitted, right? So if you find out that this patient has a high probability of readmission, what do you do about it? Well, again, the predictive model is helpful of itself, right? It rather suggests like we just shouldn't send them home yet because they're going to come back. But wouldn't it be nice if we had the tree interpreter and it said to us the reason that they're at high risk is because we don't have a recent EKG for them, and without a recent EKG, we can't have a high confidence about their, cardiac health. In which case, it wouldn't be like, well, let's keep them in the hospital for 2 weeks. It'll be like, let's give them an EKG.
True.
Okay? So there's this.
This is like the applications he's discussing are actually really useful, and like it makes me happy. But there are a lot of applications that want to over optimize workers, but the things he's talking about is about taking care of people, and it's making my heart grow a few sizes. Yeah.
There's this interaction between interpretation and predictive accuracy. Okay?
So correct me if I'm wrong, but what I'm understanding you saying is that the predictive models are a really great starting point, but in order to actually answer these questions, we really need to focus on the interpretability of these models.
Yeah, I think so. And more specifically, I'm saying we just learned a whole raft of random forest interpretation techniques, and so I'm kind of trying to justify why, right? And so the reason why is because actually maybe I'd say most of the time the interpretation is the thing we care about, and
okay,
you can create a chart, or a table without machine learning. And indeed, that's how most of the world works, right? Most managers build all kinds of tables and charts without any machine learning behind them.
Mm-hmm.
But they often make terrible decisions because they don't know the feature importance of the objective they're interested in. So the table they create is of things that actually are the least important things anyway. Or they just do a univariate chart rather than a partial dependence plot, so they don't actually realize that the relationship they thought they're looking at is due entirely to something else, right?
Good point.
So, I'm kind of arguing for data scientists getting much more deeply involved in strategy and in trying to use machine learning to really help a business with all of its objectives, right? There are companies like dunnhumby is a huge company that does nothing but retail applications with machine learning. And so I believe there's a dunnhumby product you can buy which will help you figure out if I put my new store in this location versus that location, how many people are going to shop there. Or if I put my diapers in this part of the shop versus that part of the shop, how's that going to impact, purchasing behavior or whatever, right? So I think it's also good to realize that the subset of machine learning applications you tend to hear about, in the tech press or whatever, is this massively biased tiny subset of stuff which kind of Google and Facebook do, whereas the vast majority of stuff that actually makes the world go round is, these kinds of applications that actually help people make things, buy things, sell things, build things, so forth.
Okay.
So about tree interpretation, the way we looked at the tree was we manually checked which feature was more important for particular observation. But for businesses, they would have huge amount of data and they want this interpretation for a lot of observations. So how do they automate it?
I don't think the automation's at all difficult. You can run any of these algorithms looping through the rows or doing them in parallel. It's all just code. Am I misunderstanding your question?
Is it they set a threshold that if some feature is above, for different people will have different behavior?
So yeah, okay, I get it. It's a good question. the important thing, this is a really important issue actually, is the vast majority of machine learning models don't automate anything. They're designed to provide information to humans, right? So, for example, if you're a point of sales, customer service phone operator for an insurance company, and your customer asks you, why is my renewal $500 more expensive than last time? Then hopefully, the insurance company provides in your terminal a little screen that shows the result of the tree interpreter or whatever, and so that you can jump there and tell the customer, like, okay, well, here's last year you're in this different zip code, which is less has lower amounts of car theft, and this year also you've actually changed your vehicle to a more expensive one or whatever. Right? So it's not so much about thresholds and automation, but about making these model outputs available to the decision makers in an organization, whether they be at the top strategic level of like, are we going to shut down this whole product or not, all the way to the operational level of like that individual discussion with a customer. So like another example is like aircraft scheduling and gate management. Like there's lots of companies that do that, right? And basically what happens is that the people, there are people at an airport whose job it is to basically tell each aircraft what gate to go to figure out when to close the doors, stuff like that. And so the idea is, you're giving them software which has the information they need to make good decisions. So the machine learning models end up embedded in that software to kind of say like, okay, that plane that's currently coming in from Miami, there's a 48% chance that it's going to be over 5 minutes late. And if it does, then this is going to be the knock-on impact through the rest of the trip.
Whoa, I was about to ask, like, why do we need a machine learning application for scheduling? Because, like, scheduling is pretty, like, clear to write code for. But now he's talking about knock-on effect of things being late, which is, like, obviously in airports, probably nothing is clear 100%. That's pretty cool.
Terminal, for instance. Okay. So that's kind of how these things tend to fit together.
Okay.
So there's so many of these.
Wow.
Right? There's lots and lots. And so it's not like, I don't expect you to like remember all these applications, but what I do want you to do is to like spend some time like thinking about them. Like sit down with one of your friends and like talk about a few examples of like, okay, how would we go about like doing failure analysis in manufacturing? I don't know, like, who would be doing that? Why would be they doing it? What kind of models might they use? What kind of data might they use? Like start to like kind of practice this and get a sense. So, because then as you're like interviewing, and then when you're at the workplace and you're talking to managers, you want to be like straight away able to kind of recognize that the person you're talking to, what are they trying to achieve? What are the levers that they have to pull, right? What is the data they have available to pull those levers to achieve that thing? And therefore, how could we build models to help them do that? And what kind of predictions would they have to be making, right?
Okay.
And so then you can have this really thoughtful, empathetic conversation with those people, kind of saying like, hey, in order to...
I guess talk to them about the things that are important to them and not be just the person behind the screen.
Reduce the number of customers that are leaving, I guess you're trying to figure out like, who should you be providing better pricing to or whatever, and so forth.
So what I'm noticing, like from your beautiful little chart above, is that like a lot of this, to me at least, still seems like the primary purpose is like at least the base level, like is predictive power. And so I guess my thing is like for explanatory problems, like a lot of the ones that people are faced with like in social sciences, is that something machine learning can be used for or is used for, or is that not really the realm that it?
Sure.
Yeah, it's,
sure.
That's a great question. And I've had a lot of conversations about this with people. And so
Explanatory versus prediction.
Social sciences. And currently, machine learning is not well applied in like economics or psychology or whatever on the whole.
Okay.
But I'm convinced it can be for the exact reasons we're talking about. So if you're trying to figure out like you're trying to do some kind of behavioral economics and you're trying to understand like why some people behave differently to other people, you know, a random forest with a feature importance plot would be a great way to start. Or like more interestingly, if you're trying to do some kind of sociology experiment or analysis based on a large social network data set where you have an observational study, you really want to try and pull out all of the sources of kind of exogenous variables, you know, all the stuff that's going on outside. And so if you use a partial dependence plot with a random forest, that happens automatically. So I actually gave a talk at MIT a couple of years ago for the first conference on digital experimentation, which was really talking about like how do we experiment in, you know, things like social networks and kind of these digital environments. And yeah, economists all do things with like, you know, classic statistical tests. But the group of yeah. But anyway, in this case, the economists I talked to were absolutely fascinated by this, and they actually asked me to give a introduction to machine learning session at MIT to these various faculty and graduate folks in the economics department. And so
That's really cool.
and some of those folks have gone on to be, you know, write some pretty famous books and stuff, and so hopefully it's been useful. So like it's definitely early days, but it's a big opportunity. But as Yannet says, it's you know, there's plenty of skepticism still out there. All right.
All right.
Well, the skepticism comes from unfamiliarity, basically, with like this totally different approach. So like if you've spent 20 years studying econometrics and somebody comes along and says, you know, here's a totally different approach to all the all the stuff that econometricians do, you know, naturally your first reaction will be like, prove it, you know. So that's fair enough. But I think it's, you know, over time, the next generation of people who are growing up with machine learning, some of them will move into the social sciences. They'll make huge impacts that nobody's ever managed to make before, and people will start going, wow. You know, just like happened in computer vision, right? When, you know, computer vision spent a long time of people saying like, hey, maybe you should use deep learning for computer vision. And everybody in computer vision is like, prove it. You know, we have decades of work on amazing feature detectors for computer vision. And then finally in 2012, you know, Hinton and Krajewski came along and said, okay, our model's like twice as good as yours. And, you know, we've only just started on this. And everybody was like,
Hinton, Jeffrey Hinton, I don't know about the 2012 thing he's talking about, but I know about 2014 with the ImageNet and AlexNet and all that. I read that quite recently somewhere.
Oh, okay, that's pretty convincing. Nowadays, every computer vision researcher basically uses deep learning.
Yeah.
So I think that time will come in
social sciences.
in this area too.
Okay.
Okay, I think
okay, it's the okay time where we change subject, and I also changed subject to say this is it for today, I think. This was fun. I was mostly quiet because I was listening to him discuss the things, and I feel like I didn't really have much to say, so I didn't add to the conversation at all. If that was boring, apologies. I also try not to thank you. I try not to, you know, interpret no, not interpret, interrupt. Wow. Brain, where did you go? Interrupt the lesson sometimes, because I mean, I don't mind talking, but if I don't have anything to say, then I shouldn't. Yeah. Now my brain is thinking, you're not transforming this. You're just, I'm really not a reaction channel. I'm a learning live channel. I don't know if that's, I don't know what's the difference. Yeah. Do reaction channels, yeah, there are learning related things in there. Anyway, we're not here to judge, we're just here to enjoy. Okay, so this was fun. Thank you for being here. Let me know if you have any questions or points. Otherwise, I gotta run. Let me show you something. I'm sure you've seen it, but if you haven't, then you will see it now. I updated the going to my channel, going to community tab, and then sharing the screen again. So yeah, I updated my schedule. Yesterday I wrote this schedule thing where today's Monday, we're doing a fast.ai live lesson, or lesson live, and then there will be another one on Wednesday. Hope? What about Hope? And then Friday will be another live lesson. And then the idea is on Saturdays for me to, try my hand at Kaggle competitions. Nothing serious. Probably just introductory things. There's a tiny... Yes! Yes, I saw the... the typo when I tried to post the same thing on Twitter. I fixed the typo on Twitter, but not here. Yep. I didn't do it on purpose though. Yeah. Okay. So that's all. Have a lovely rest of your day today. And see you the day after tomorrow. That's it. Let me know if there's anything on your side. Otherwise, thank you. Otherwise, we're going to end this really chill, no issue stream. Alhamdulillah. Sorry. Inshallah. I will end it starting with 5 because I think the time lag is pretty good. So yes, thank you. I really appreciate you being here and learning with me, and I hope you're benefiting from this as much as I am, or more, definitely more. Okay, I will end the stream in 5, 4, 3, 2, one day we'll get to the moon, but not today. Maybe we'll predict the moon phases or something. I don't know. Bye. Thank you so much for being here, and bye-bye.